Imagine you're holding a tennis ball. You know exactly where it is, right? It's not in two places at once, and it's certainly not floating in some weird, undefined state. But what if I told you that, at the microscopic level, things don't work that way? Welcome to the bizarre world of quantum mechanics, where particles can be in two places at once, can exist in multiple states, and don't decide what they are until you look at them. For centuries, scientists believed in classical mechanics, which describes how everyday objects move. This was thanks to Isaac Newton, who gave us the laws of motion, and James Clerk Maxwell, who explained how electricity and magnetism work. Everything seemed predictable and logical, until the early 1900s, when quantum mechanics turned everything upside down. Quantum mechanics was developed to explain things that classical mechanics couldn't, like why electrons don't fall into the nucleus of an atom or why light sometimes behaves like a wave and other times like a particle. But while quantum mechanics is incredibly powerful for making predictions, it also leaves us with one very big question: what is actually happening? Scientists have different opinions on this, leading to various interpretations of quantum mechanics. The two most famous ones are the Copenhagen Interpretation and the Many Worlds Interpretation. Let's break them down in a way that makes sense. To understand these interpretations, we first need to talk about superposition. Imagine a coin spinning in the air. While it's spinning, it's not just heads or tails, it's kind of both at the same time. But the moment it lands, it picks one state, either heads or tails. In quantum mechanics, particles can exist in superposition, meaning they are in multiple states at once until they are observed. This is what makes quantum mechanics so weird compared to everyday life. If classical mechanics worked the same way, you could be in your house and at school at the same time, until someone looked at you and found out where you actually were. This brings us to one of the biggest questions in physics. What happens when we observe a quantum system? How does it go from being in multiple states at once to just one? That's where the interpretations come in. The Copenhagen Interpretation is the most widely taught explanation of quantum mechanics. It was developed in the 1920s by Niels Bohr and Werner Heisenberg in Copenhagen, Denmark. Key idea: measurement decides reality. According to this interpretation, a quantum particle doesn't exist in a definite state until it is measured. In other words, before you look at it, it's not just unknown, it actually exists in multiple states at once. The moment you measure it, the superposition collapses into a single reality. To make this concept easier to understand, physicist Erwin Schrödinger came up with a famous thought experiment, Schrödinger's cat. Schrödinger's cat experiment. Thought experiment. Imagine you have a box with the following items inside. 1. A cat face. 2. A radioactive atom, which may or may not decay. 3. A Geiger counter, to detect radiation. 4. A hammer attached to the Geiger counter. 5. A vial of poison skull and crossbones. If the radioactive atom decays, the Geiger counter detects it, the hammer smashes the poison vial, and the cat dies. If the atom does not decay, the cat remains alive. Since radioactive decay is a quantum process, it follows quantum rules. Before we check inside the box, the atom is both decayed and not decayed, meaning the cat is both alive and dead at the same time. But when we open the box and look, we see only one outcome: the cat is either alive or dead, not both. According to the Copenhagen Interpretation, the act of looking forces the universe to pick one reality. This is called wave function collapse. Problems with the Copenhagen Interpretation. This explanation raises some difficult questions. 1. Why does observation collapse the wave function? 2. What counts as a measurement? 2. Does it have to be a person? A camera? A machine? 3. Why do quantum particles behave differently when they are observed? Some scientists found these ideas unsatisfying, so they proposed alternative explanations. One of the most famous is the Many Worlds Interpretation. In 1957, physicist Hugh Everett suggested a mind-blowing alternative. What if both possibilities always happen, but in different universes? Key idea: the universe split according to the Many Worlds Interpretation. When you observe a quantum system, the wave function doesn't collapse. Instead, it splits into multiple realities. Every possible outcome happens, but each outcome exists in a separate universe. Schrödinger's cat in many worlds. Let's go back to the Schrödinger's cat experiment. In this interpretation, 1. There isn't just one reality where the cat is alive or dead. 2. The universe splits into two versions, one where the cat is alive and one where the cat is dead. 3. You, the observer, also split. 3. In one universe, you see a living cat. 3. In another universe, you see a dead cat. Every time a quantum decision happens, the universe branches into multiple realities. Right now, there could be countless versions of you living out different outcomes. Problems with the many worlds interpretation. While this interpretation solves the problem of wave function collapse, it introduces new problems. 1. Where are these other universes? 2. Why can't we detect them? 3. What causes the splitting? One idea used to explain this is quantum decoherence, the process where different quantum states become separate and stop interfering with each other. But since we have no way to directly observe other universes, this remains speculation. Which interpretation is correct? The truth is, nobody knows which interpretation is correct. Scientists can use the equations of quantum mechanics to make incredibly accurate predictions, but the underlying reality remains a mystery. Here's what we do know. 1. The Copenhagen interpretation is the most commonly taught, but it has unexplained problems. 2. The many worlds interpretation is mathematically consistent, but unprovable. 3. Other interpretations exist, such as the pilot wave theory and objective collapse theories, but none have been universally accepted. The quantum mystery continues. Quantum mechanics works. It powers everything from lasers to computers to MRI machines. But how it works is still up for debate. Maybe one day, we'll uncover the true nature of quantum reality. Until then, all we can do is explore the different interpretations and keep asking big questions about the universe. So what do you think? Does measuring reality create it? Or do infinite worlds exist, with endless versions of ourselves? Let us know in the comments below. If you enjoyed this video, don't forget to like, subscribe, and hit the notification bell for more fascinating explanations of science and the universe.